This is CSAP's Science and Policy Podcast from the University of Cambridge, where we're bringing you the latest evidence and expertise to improve public policymaking. Welcome, I'm Rob Doubleday, presenting this week's episode of CSAP's Science and Policy Podcast. This week we're pleased to welcome Professor Clare Grey and Professor Martin Rees to join us to discuss questions about how science and innovation can contribute to policy goals to address climate change and meet net zero targets. So today we're joined by Professor Clare Grey, who's a Royal Society Research Professor and Professor of Chemistry at the University of Cambridge. Clare Grey's research has broken new ground in understanding the physical characteristics of materials that are used in batteries. Clare Grey is also a principal investigator in the Faraday Institution, which is the UK government's major investment into new battery science. So Clare, very welcome. And we're also joined by Martin Rees. Lord Rees is the Astronomer Royal. He's an astrophysicist and cosmologist, past president of the Royal Society. And Martin, you've been very vocal recently about the important role the UK can play in contributing to global climate change targets, particularly through research and innovation. And so we're interested to hear your views about the UK contribution to the global effort in science and technology. But I'd like to begin perhaps by asking Martin what you feel about the role science and innovation should play in addressing the climate change targets. I mean, some people argue that it's really a technological and economic and social challenge, and we need to act now, and we kind of know what to do. But what do you think science can contribute?
Well, I think before that, we've got to emphasize that the public has to be on side and regard it as important to reach carbon zero by 2050, which is a declared target. And it's frankly not going to succeed if the public doesn't prioritize it and doesn't accept its importance. And I think it's a big ask if people are going to think they're going to make sacrifices for this. So the line I would take is that we can have a win-win situation if our main focus in the UK is in trying to do the R&D needed to provide more efficient modes for clean energy generation and storage and distribution via smart grids. All these technologies, they're exciting. They offer frontier problems in science and technology. And moreover, I think it's another reason why it's politically good to do this. First, if the UK can get a lead in some of these technologies, it's an economic plus. And secondly, it's good for the world because after all, even if we meet our targets for 2050, then our net emissions are less than 2% of the world's emissions. So it doesn't make much difference to the world's climate, whether we meet our targets or not. However, we do have a potential leverage and amplifying effect if by our actions in collaboration with other nations, we can accelerate R&D so that the cost of clean energy comes down, so that in particular is competitive with coal. So that a country like India and maybe nations in Africa, which actually need more energy per capita if they're going to develop, don't feel they need coal-fired power stations, but can leapfrog directly from burning smoky stoves and wood and dung in their homes to clean energy. If we can help that, then we can make probably 15 or 20% difference to the world's emissions, because their potential emissions in those hugely populated countries which are developing are far, far more than ours. So I think it's more important for the world and for our economy that we should do that. And moreover, I think if we want to encourage young people to go into this area, then there are a few more inspirational goals for young engineers than to help to provide clean and affordable energy, not just for us, but for the developing parts of the world. There are more positives and more chance of getting public support for a massive program to expand R&D into the forms of clean energy where the experts feel that we have a head start.
But so, Martin, you wouldn't argue that should then be that one might want to set an example, for example, in different transport networks and cities, and not just in the R&D, because I sort of feel like that 2050 agenda isn't going to be achieved just by technology. It's also going to have to involve changes in the way that we live. And I think we have to try. I appreciate what you're saying. That
I agree with that. And I think we should do all those things to make our life better, to make better lives in particular for those who are underprivileged now. But I think if we want to ask what will actually help the world, rather than just the UK, then we have far more leverage if we can help the major developing countries to develop clean energy. Because unlike us, and as you rightly say, we can economize on energy and get by with less per capita consumption. I don't think we can tell the Indians that. I think they're going to need more. And we've got to make sure that the extra energy which they need is of a kind which is non-carbon producing. So I still think that the goal of providing clean energy is more important for the world. Although for us to meet the targets, I completely agree that we'll have a hard job meeting them without the societal changes and changing our style of transport and cities, etc., which you mentioned.
But of course, those sort of societal changes and different urban planning can also roll out to other parts of the world as well, because it's also the engineering, it's the demonstration projects and showing how these things can be done.
Yes, and I think so. And if I could mention something which I think is very helpful is what Jeremy Allwood and his colleague have done in Cambridge about moving towards a circular economy, pointing out that, for instance, the girders in a building are reusable when the building's demolished, and you can't make them thinner anyway. And so there are lots of ways in which we can save raw materials and energy in our construction, in our roads, in our transport, and everything else. So I think it needs to be something which we consider on a broad front. But that's not going to directly benefit the rest of the world unless we have clever technologies in those areas.
If we take Martin's opening statement for a moment anyway, and then think, well, Claire, you as a scientist working at the forefront of some of the science and technology to do with energy in the UK, where do you see the contribution that science and research in the UK could make to the energy transformation that's needed, not just in the UK but in the world? Where do you see the scientific opportunities?
Well, I wanted to sort of follow on from one of Martin's comments to make another one which sort of feeds into your question. I mean, the problem is it isn't just a UK activity. The challenges to meet some of the 2050 targets are going to require inventions and innovations that are global. And I don't really think we can come up with a policy that's siloed in the UK. It doesn't make sense. I mean, that's not how science is done. And obviously Martin knows this. So that was my first point, that I don't think an energy policy, a science energy policy can only be a UK one, because
I agree.
It's a real challenge to do to make impact in these areas. And that's also how science is done. And that's the best science is always done globally. And I think we need to remember that when we enter a period politically where the UK is pushing away from Europe, science is, we have massively appreciated our European partners, and from the very practical things like using synchrotrons, which are these high X-ray sources. We have one in the UK, but we have one in France. And so it's the equipment, but it's also the people and also the talent. We have young scientists who come all around the world, and we train them and they go back to where they've come from, but we also use them and train them, and we benefit from those interactions. So yeah, that would be point number one. Point number two is that I work in batteries, and there are significant challenges all across the place. We have batteries that are reasonable for electric vehicles, for cars, but the challenge is, how do you do that for lorries?
So can I ask a question, Claire? I mean, again, for a general audience, to try and understand what contribution is energy storage going to play to the kind of energy transition that's going to be needed to meet climate change goals. I mean, try and paint a picture for people about how important is storage as part of the overall system.
So storage has got two roles. One is in transport, and that's about in the first instance, reducing pollution, so reducing emissions. The second one is more efficient use of fuels. So in the sort of short term, you're still using petrol, but in a hybrid electric vehicle, and you're being more efficient, but then you're transitioning eventually to an all-electric vehicle. And so that's about increasing the use of electricity, and that then works if your electricity is then produced in a renewable, zero carbon way. And then you start asking the question, how are we going to do that? And then you get onto the grid scale storage, and then there, as you increasingly use more renewables, you have a problem of intermittency. So in the UK, of course, the sun doesn't always shine and the wind doesn't always blow. And it's that problem of dealing with intermittency. And so we can deal with intermittency to a degree by building wires that go across to Norway, across to our partners to balance the grid. But a lot of the wind farms have similar weather patterns. So you can have periods in February when there's very little wind. So how do we store? So we've got problems of storage in the short term and the long term. And the batteries play a role at the moment in short term storage. So the sun goes behind a cloud. You've got to be able to provide electricity very quickly. You come home at 6 p.m, you put your kettle on. That's the period of the day where there is a maximum overlap between industrial energy and residential energy use. So you've got to do some energy balancing there. And there's a market associated with being to have storage and then selling it to the grid in those periods of peak energy demands. And then that allows you to put these quite expensive batteries on the grid and still make money. And then there's issues of frequency generation for dealing with the frequency responses. And I think batteries are more or less fit for purpose. And you're seeing these demonstration projects go in where you will have a battery storage as being bid as part of that. The challenge now is how do we do something and deal with storage for the much bigger periods of, I wouldn't say even intermittency, it's be zero renewables on the grid. And their batteries are really a challenge.
When you say short term and long term, I mean, how short is short term and what's that going to look like? And what are these batteries going to look like that are doing this short term job of
the short terms are dealing with the very short, you have a power outage and something, you might have a battery pack in your hotel or something, or where it's the power goes out. But typically these are the 20-minute time periods before you have an alternative storage. At the moment you'd have gas turbines on as backup, and they would take 20 minutes to ramp up. You might have a base load in the UK of nuclear, but those are sort of continually running. So it's and then now we have a multitude of different other sources of energy on the grid, but you could imagine moving to more gas turbines that have a finite period before they switch on. So that's what I would call short term. Although there are others who would say even more short term ones are dealing with spikes and frequency fluctuations, and those would be even shorter.
And what about, as grids becomes increasingly smart and batteries, as you said, in cars and in our homes become increasingly ubiquitous, are there other ways of balancing the grid that don't require so much storage, just by additional storage, just by different bits of the grid talking to each other more effectively? Or is that not such a plausible scenario?
I think you can get something out of being smarter, like many things in life. But ultimately, you still have a problem where you do have to have reserve capacity and storage. We can have a separate discussion about cars on the grid. I know that there are people who think that they are going to be a part of the whole storage system. I think that they will bring extra demands on the batteries, but because you will have to cycle your batteries more often. And if you think about it, a Tesla, which is just represents sort of an example of a very high-end car that many of us wouldn't necessarily want to spend that much money buying, you might be able to justify it if it was part of selling it to the grid. If you're at the lower end car where your car has a range of 150 miles, in order to use it on the grid, you're cycling it a lot. And so there then become issues in terms of longevity of your car battery. If you're also cycling, and a Tesla at 300 miles would be maybe charged once a week. And so that's part of the reason why those batteries last a long time. So I think there are other consequences, but then there may be people or the economics may become viable for some people and not the other. But I sort of feel like the car thing is sort of an irrelevancy. It helps to a degree, but ultimately for 2050, we have to have bigger ways of storing than car batteries.
Could I ask Claire a question about capacitors and what the difference is between the virtues and otherwise of capacitors and batteries?
Well, capacitors are batteries that charge very fast. From a science level, they're subtly different in that they're made up of activated carbons, and that the way they store charge is fundamentally different. But the reality of is batteries are now being designed so that they can charge so fast that they are coming into the supercap space, but they have much higher energy density. And a disclaimer, we've just found a new company on fast charging of batteries, so I should declare my conflict of interest there. But I think others would also agree with me that we are entering a space where the supercaps are going to be, I wouldn't want to go on, I'm obviously going to go on the record, where they're going to become less important. Mm-hmm. They will still have their roles where you want cheap, fast power, but in large-scale storage, I think you're going to get to the point where you're going to build a battery. You ultimately want more energy density, and you can get that even if your battery isn't quite as good by just having a bigger battery, and then you can still charge it fast. That's how, if you look again at these high-end cars that are claiming that you can do fast charging, they're not doing it by some amazing battery technology. They're doing it by having a bigger battery so that you don't stress the battery as much.
So Claire, can I bring you back to the longer term storage on the grid? I think you've made the case very clearly for why this shorter term storage over sort of minutes, up to 20 minutes, is needed. But what's the role for the longer term storage on the grid?
There are a diversity of opinions on this, and there are some who say just keep on building, put more and more battery packs together, and you get a big enough battery. Those batteries start to become the size of not quite hydroelectric plants, but they're monstrous. And I think if you look at, even if we just take cost out of the equation and we don't think about for a few minutes who's going to pay for it, who's going to deal with the embedded costs associated with that. Just think about the resources. At the moment, we're already worrying about the cobalt and the nickel for the electric vehicles, and then just scale it up by an order of magnitude or even 2 orders of magnitude. And so then you can say, okay, well, what about making things cheaper? Or where do we come up? Can we come up with new materials? So we could replace the lithium by sodium. That's a reasonably straightforward swap. Again, and we could probably find some compounds that have more iron in them as opposed to cobalt and nickel. So there are more sustainable ways of doing it, but they're still not mainstream. But I think ultimately the problem is it's such a big problem. And I just think that the best way to store energy is in a fuel. To articulate this from the perspective of a non-scientific expert, you have amount of stuff and you can only get a certain amount of electricity out of an amount of material. And the most effective way of storing energy is actually in a carbon-carbon bond or a carbon-hydrogen bond. So I think that as we move forward, the battery will start to become more closer to what's known as a fuel cell, where we're starting to use some of the ideas of a traditional fuel cell where we exact hydrogen and oxygen to make water. And we do this reversibly, but we use alternative fuels in a sustainable fashion. So that would be one way. And we use these batteries called redox flow batteries, which are a bit like fuel cells, which can be much bigger. And the other alternative is we give up on batteries and we do things like compressed air storage, more hydro, lots of different things. I don't think at the moment there is a battery that can do grid storage. And I think this goes back to Martin's thing. We have to keep on pushing the research. And I think we have to think about what are our energy vectors that we're going to use. And is a traditional battery that we see in 2020 the battery that's going to be our grid storage battery in 2050? And I would say we don't know what that one is yet.
So, that's an interesting question as well for you, Martin. How, given that, really kind of exciting scientific agenda that Claire's set out for grid storage and the role of batteries or fuel cells, how do you think science could be organised to address that sort of challenge?
Well, I think some of the science is sort of fairly small scale that can be done in university labs. But there are some projects, I mean, obviously nuclear, particularly fusion and things like that, which deserve some kind of investment, and that's not appropriate for university. That should be done, in my opinion, in some sort of government lab. And Peter Littlewood, who was head of the Cavendish here in Cambridge and then went to run the Argonne National Lab in America, is an advocate of government labs, rather as Steve Chu was when he was Energy Secretary in the US. And of course, we do have successful government labs in agriculture and of course in the MRC. And I think that perhaps we need some of those with a mixture of public and private funding. But this is pre-competitive research on basic big ideas. I mean, fusion's at the extreme of something which is very far from the market, but where we think is worth supporting the spherical tokamak column, for instance. But in between, there are probably areas where it's too much for university to do by itself, but there should be some sort of institutions. And again, I'm not an expert. And of course, Claire's quite right that these should be internationally, pan-European or jointly with India, etc., as appropriate. But I think we've got to realize that some of these developments are going to be long-term. And of course, we haven't said much about nuclear, which, as Claire pointed out, is a sort of base load which you can't turn on and off very quickly. And I personally think we ought to have R&D into all fourth generation types of nuclear design in the hopes that they are going to be safer and more flexible and hopefully cheaper than the nuclear power stations we've been building up to now, which are based on 1960s technology and of course are expensive because each is almost one of a kind and there's no mass production. So I personally think that we're handicapping ourselves if we don't consider nuclear as part of the mix.
I mean, I think we need to reflect on, though, what our national lab would look like. I mean, I think, so I spent, as you know, almost 20 years of my life in the US and was funded for a long time from the Department of Energy and work with people in these national labs. And I think you can look at the ones that worked well and the ones that didn't work well. And I think the ones that, in a way, were most innovative had very strong links with universities. And I think that's also the same with the MRC in Cambridge. Mm-hmm. That environment, I mean, I don't know whether they disagree or agree, but they're very much enriched by being where they are. And I think if you plonk an MRC in isolation, then it doesn't do a very good job. And I think that proximity meant that there was a flux of PhDs and postdocs, and that vibrancy that comes with people moving in and out of science is very important.
Yes.
So
I completely agree with that. But my point is that they need to be people who are encouraged to do long-term research, don't have to be pressured by the constraints of the ref to produce a certain number of papers per year, etc., and have fewer distractions than academics do. And I think we see that some of the best research in this country, even though we are a country which prides itself on its research universities, the best is done in the MRC lab and in places like the John Innes Institute, where David Balcombe did his classic work, etc. So there is a role for labs which could do long-term, full-time research in societal problems.
No, well, I sort of agree, although I think in the US, a lot of the good science is not necessarily done in the national labs. Mm-hmm. I mean, there's a Bell Labs model that Steve Chu was strongly influenced by because he came from Bell Labs.
Yes.
That was a particular era of an industry that had essentially a monopoly on its area, and so it was able to fund for a long time this research, and it was obviously very successful. And I think, how do we emulate that? I mean, and I think, as an academic, I too would quite like on longevity in my funding, and I think that would go quite a long way to doing that. And you could look at the French system, where they tend to put sort of a national lab embedded in the university. Not sure that works that well in the French system either. So,
Claire, taking the example of developing radically improved solutions for longer term storage on the grid, as a sort of scientific and technological challenge. And given that the UK government is committing to seeing a considerable increase in the amount of money from public and private sector spent on research and innovation, how do you think the UK should organise its research to contribute to that challenge which you put out? Given we're starting from where we are and have the mix of research funded in the way it's funded in the UK, which does predominantly focus on university research as a place that public funding for research goes, how do you think it could be best coordinated to address some of these really big long-term scientific and technological challenges in society's interest?
I mean, one of the challenges at the moment is I don't think we know what the solutions are. We don't necessarily know what the energy vectors are. And so I don't think we can afford to specialize at this point. I still think if you look at the 2050 agenda, I mean, if you want to think about a battery that's going to be relevant for 2030, we have to be doing it now. For 2050, we still have the time to be innovating. And the challenge with, if you look at the next generation of batteries, whether it's a redox flow one or whether it's a lithium sulfur or lithium oxygen batteries or lithium air batteries, is where you react with lithium and oxygen to form the lightest product ever. And that's the battery with the energy density that is comparable to that of gasoline. There are still significant showstoppers and things that we don't know how to solve. And so when you have that sort of challenge, it's difficult to develop a sort of development type project. It really still has to be fundamental research. And then you've got to step back and say, okay, what are the challenges? How do we get there? And then ask the question, how much of it is exploratory and blue skies in order to do it? And how much of it is directed to a problem? And so, I mean, I'm very personally interested in the ideas of controlling materials that are out of non-equilibrium environments. So, and that it doesn't really matter if one doesn't understand what I'm saying, but that has implications on the way that one might bring different types of scientists in to attack those problems. I think one can identify the different challenges and then set roadmaps as to the types of things that are needed to do to enable it. I think we in the UK need to be much better at thinking much harder about our science and how we're going to do it than in some ways we are. I mean, when I was in the US and we ran a couple of Department of Energy workshops where we spent a lot of time reflecting on really where the challenges were and what would be needed. And I think if we're really going to set ourselves with a 2050 agenda and we're going to do it properly, we should be doing more of that. And I could articulate the same thing for the hydrogen economy. I think there's some bottlenecks, and we need to understand whether we can even achieve those bottlenecks. I mean, if you take water electrolysis, there's an overpotential. What that simply means is you've got to put more voltage in to get something out. It doesn't operate at the maximum efficiency, and we need to understand, could we ever achieve that, and what would we need to do in order to do that? So I would say step A is to actually be more critical about what researchers need and how we're going to do it, and then we have to sort of assemble the teams and work out the timescales of it and go from there. So for me, that would be an important first step.
The main point is it requires organisation on a level larger than a single university. So you can't just leave each university to do its own thing. You've got to have agreed policies about priorities and make sure that they're supported long-term if necessary. Sure.
And then you've also got to have, I mean, to be honest, you've got to have a carrot. You've got to at least dangle the front of the academics and the students and everybody involved, that by doing this, there is a real potential that there will be some funding coming down the road and that is worth their time and effort to really be creative and think about how to do it. And I mean, that's the reality of all human beings, is that certainly helps.
So what might the future of innovation look like in the UK?
I mean, we're talking about innovation and new industries where we don't actually always have the industries in the UK. So where are these magic leaders who are going to inspire us? I mean, there may be, and obviously, because there are obviously lots of wonderful industry leaders, but it's not apparent that if we want innovation, we need to be reaching out to the industries that we have currently. We need to be innovating new industries, and we can have a discussion about how we move innovation in national labs and in academia into the marketplace, which I think is another whole conversation. But it's not obvious to me that we need an industrial-led activity. And I think one of the problems of Innovate UK, in my limited experience, is that operates with a consortium of industries and only a little bit of money goes to academia. And that works when you have industry partners where each industry has a different role to play. But you can't put two battery companies to work together with an academic to make a better battery because they're in competition. But if you have different parts of different sectors where different people need different components, then they may work together. But it doesn't necessarily lead to the most innovative work of the 2050 type time frame. It is about solving the short-term things. And I think it's useful for academics to be a part of those types of projects because you get some sense of, the whole follow through, all the different TRL levels. But I'm not sure it's a way of speeding up dramatically translation.
I agree.
Yep.
Okay. To sort of wrap up, maybe we could get sort of concrete with respect to the Faraday Institution. And it'd be interesting to hear what's working best about Faraday Institution and what's your experience. Is it adding, what is it adding to the UK research scene at the moment?
Well, I think I'd sort of stick to my experience with my own project. So I look at extending battery life or battery degradation. I think the first instance is really created a much broader community of people working in this area. So when I started, just to take Cambridge, for example, there were not so many people working in batteries, but we brought people into it. And then what's been nice is we've been able to pull in people with different techniques. So batteries have been around they've been around since the Baghdad battery, but the sort of ones that we would look like a battery have really been around since 1851. And we sort of view them as these rather boring things and that all the problems have been solved. Those types of thinkings about things tend to stagnate a research field. So what you need is to bring in people with different techniques and different ways of looking at things to really excite the field, excite the scientists, and convince people that actually there's some really cool science to do. And some of the challenges in batteries, like looking at an interface, so a solid liquid interface is an area where we have so much that's unknown. We don't even know how ions get from the solution to the solid and electrons go backwards and forwards, how these things survive over time. And so for me, that's what the first stage of the Faraday Institution has been about, is bringing together a bigger community, exciting them about the challenges in the field, and then also training the students. And then as part of that is also engaging a broader industry base as well. So, I think it's been exciting. It's still early days.
And finally, turning to you, Martin. So you began by making the case that focusing on some of the scientific and technological challenges that need to be met in order to tackle climate change is necessary to achieve net zero targets, but also can excite a new generation of people into science and research. Where do you see some of the most, from your view, some of the most exciting areas in energy and in energy transitions?
Well, I don't know, because I think it would depend on experts like Clare to decide where there is scope for improvements in these various technologies. But I think we've also got to think not only about what we could do to accelerate the transition in developing countries, but also what we're going to do, because are we going to depend mainly on wind power, or if we can improve the efficiency of long-range grids, could we expect to get solar power from southern Spain or North Africa in the long run? I think there are big issues like that about the balance between sun and wind, which will be different if we can plan on a pan-European scale from if we have to focus on our own country. And maybe we can have a cable along the Belt and Road to China to smooth over the peak demands at different time zones and all that. There are all these possibilities. And if we think on a big scale, one can clearly smooth over fluctuations in climate and time zones and all that and do better. So I think there's got to be some people thinking about the big picture for 2050. But in the shorter term, I do think that to ensure that young scientists feel that there is an exciting opportunity, whether their expertise in biofuels or batteries, etc., in energy, would be good for the world and indeed good for this country.
Great. Thank you both. So thank you very much for joining us today. If you enjoyed this episode, please don't forget to like and subscribe, as they say, and join us next week where we'll be talking about science policy and the green recovery with respect to cities and green infrastructure. So I hope you'll join us then. CSAP's Science and Policy podcast is a production of the Centre for Science and Policy at the University of Cambridge. This series is produced in partnership with Cambridge Zero. This episode was hosted by me, Rob Doubleday, and was produced by Kate McNeil. You can learn more about CSAP's work by visiting us on Twitter at CSciPol or at our website www.csap.cam.ac.uk. If you have any feedback about this episode or questions you'd like us to address in a future week, please email inquiries@csap.cam.ac.uk. Thanks for listening.